Welcome back to the lecture series, Applied Statistics Using Programming. Today, we're going to cover descriptive statistics, and let's get started. So Lesson 4, Descriptive Statistics. Before we talk about descriptive statistics, let's do a little bit of a review about the basics of data. So in the previous video, we talked about different types of data. A variable, which is a set of attributes. An attribute is a characteristic of an object or a person or a thing. In the previous video, we talked about the ratio scale, interval scale. We also talked about the ordinal scale and the nominal scale. For more information about these data types, please review the previous video in this lecture series. Now, previously, we've mentioned a bit about vectors and data frames, so let's review a little bit and classify the different data structures that are often used in R. Most simply, we have a vector. Vectors are used for analyzing columns or variables. A matrix is a bit more complex. A matrix is a two-dimensional array, and what this means is you have rows and columns. However, the limitation of using a matrix is that it only allows one data type for all rows and columns in your matrix. An array is a multi-dimensional matrix. However, it suffers from the same limitation as a matrix, which is it can only accept one type of data for the entire matrix. In other words, we cannot have mixed data types. So, something more useful is a data frame. A data frame is like a matrix. It has two dimensions, columns and rows. However, each column can have a different data type than the other columns. In other words, we can use mixed data types for different characteristics of our data. Finally, lists are much more flexible. Lists are very useful for unstructured data. However, mostly when we're using statistics in this course, we'll be looking at tabular data. In other words, data frames and vectors are much more useful for statistics in the sense of this course. However, other data structures exist in R that can be useful in certain circumstances. Lists can be very useful for dealing with text data. For example, if you're looking at online reviews of restaurants, you may have some restaurants with many reviews that are very long and other restaurants with many short reviews or no reviews at all. In this case, a tabular structured data set, like a data frame, is not very suitable for this type of structure of data. So a vector is a one-dimensional string of data. For example, we can make a vector using the C function for concatenating many different values together. And when we concatenate those values, for example, 1, 2, 3, or A, B, C, the sequence is important. The first value is the first value. The second value is the second value. It retains the information of the sequence that we make our vector with. We can make a vector using many different data types. So for example, this A example here is using numeric data, specifically integer data. B, we're using string or character data. C is using a factor, which is categorical data, categories or groups of something. And in D example, we have a vector made of 3 different date format values. As we mentioned, matrices can also be used. Matrices can be very useful if we're dealing with one data type. Specifically, it's very useful for numeric data type. But if we're using different formats of data, matrices have a limitation that we cannot use different data types with them. The same limitation applies to arrays. However, data frames solve this problem by allowing for multiple data types for each column. The list structure can also be very useful for unstructured data. So first, what is this code doing? We have a value, 1, and we have the function class. What does the function class do again? It tells us what data class we're dealing with. So this code here is telling us that 1 is numeric data. The next example, quite simply, we have the value A in quotation marks. And if we run this, this is going to tell us that we have a character class data. Now, mode is very similar to class. And you'll see that using simple data, like just an integer 1 or a character A, it's going to give us the same result as class. However, when dealing with a little bit more complex data structures, such as matrices or arrays and so on, the mode will tell us what type of content, what type of data is inside that complex structure, whereas class will just tell you what the overall type of data you have is. So for example, if we have a matrix, class will tell us that we have a matrix or array. Mode will tell us what kind of data is inside that matrix or array. Okay. str we have also used before. str is structure. So in this case, if we just have one value, it's telling us that it's numeric, and this is the first value that we have. And structure can also be used on character data. Character gets shortened to CHR, whereas numeric gets shortened to NUM. And pretty simply, it's just showing you the first value that shows up. In both of these cases, we only have one value to show up. All right, so making numeric data, there are a few ways to make some numeric data. We can use L, and that will create it as an integer. Okay. In this second case, we have 1, ... 10. This gives us all the integers between 1 and 10. So it tells us that this is an integer. In class 1.1 to 10.1, if I highlight just this part of the code and run just this part, we see that it's all of the values from 1.1 to 10.1 by adding whole numbers. So what class do we have here? We don't have an integer. An integer means there's no decimal place. We have a numeric data class. R is much more convenient than many other programming languages because R will switch seamlessly between integer data type and numeric data type. So as a user, we don't need to care too much whether it's numeric or integer because R will adjust depending on the data that we're dealing with. However, if you see that the result of your class says integer, that's telling you that you have a number with no decimal. If you have the result numeric, it's expecting a decimal as part of the numbers. Okay. Both are interchangeable. Categorical data, we can use as character, which will change the data into a character type. However, this A is already a character type, so this as character is actually not changing the data in any way in this code here. So let's use class as character. We should get character, as you might expect. The next example, if we have categorical data that is in a factor type, we get the result factor. This just means we have a categorical data that is groups or categories. So let's take a look at vectors in R. To make a vector is simply many values in a sequence. Okay, so our first sequence of values is 1, 2, 3. And to make that into a vector, we use the C concatenate function. And what that function does is it takes many values and puts them together in the form of a vector. So our first vector is A, and A is a numeric vector that's very short with just the values 1, 2, 3. In order to see my vector, what's in it, we can highlight the object A and hit enter, and the result will show you in the console below. The result will show you what are the values held in the object A. Next, we have a longer vector, AA. This is simply a longer numeric vector. Next, we have a short vector using the characters ABC. Let's just take a look at that real quick. And we can see we have the values A, B, and C, and their characters. Next, we have a longer vector called BB. And in this case, we're putting together letters. What is letters? If you remember, if we highlight part of our code in the script and hit enter, it will run just that part of the script down here in the console. In other words, if I want to see the value of a specific object or variable, I can simply highlight it up in the script, run, and see the output on the bottom. So what is the value of letters? Letters is already a vector that is pre-programmed in R that contains all of the letters of the English alphabet. Next, let's look at C. C is a vector of factor. So what is a factor? A factor is categories. If we run our code, we see down below, we see X, X, Z, the values in our vector, and we see extra information telling us that we're using a factor, which tells us the levels of the factor. Levels refers to the different categories that are in our data set. In this case, we have X and Z, so the possible categories are X and Z. Next, D is our date vector. So as you see, we use the function asDate to change a character into a date. We do that 3 times, which gives us a vector with 3 values. If we check the date, it shows us what looks like a character class, but is actually a date class, telling you the year, the month, and the day. Always in this format when it's in a date data type. In order to extract a specific value from a vector, we can use our indexing function. Indexing, we use those square brackets. So A2 refers to the second value in the vector A. The vector A looks like this, 1, 2, 3. So the second value is 2, quite easily. So how about B? Our B vector looks like this, A, B, C. So the second value, if we're using indexing, would be B. C is the same. Here we have X, X, Z. So what is the second value? On top we have our values. So the second value would be X. And again, it shows us X is that value. And on the bottom, it tells us what are the possible values that it could have taken. Finally, we have D. And D is a vector of dates. So what is the second value in this vector? It is quite simply the second value in D, which is 2026. Next, let's talk about matrices. A matrix is a multi-dimensional vector. In other words, it's like a vector, but it has 2 dimensions rather than just 1. So our matrix looks like this. Even though we still just have a vector here, we have 1 column and 1, 2, 3 rows. And if you notice, when we look at a matrix, we see the rows are formatted as follows. We have square brackets indicating that we have some sort of data. And first, before the comma, we have the row number. So this is saying this is row 1. And after the comma, if it's blank, it's all of the columns. Next, we have row 2 and all of the columns here, and row 3 and all of the columns. Up here in our header, we have a blank, comma, 1. This means blank, meaning all the rows, comma, then column number 1. In this case, our matrix is very easy because we only have 1 column and 3 rows. Let's look at a more complicated matrix. In our second example here, we have a matrix combining A and AA. So if you remember, A looks like 1, 2, 3. AA looks like many different values. So can we just concatenate them here? What happens when we concatenate two vectors, it puts the two vectors together. But we're also using the function called matrix, and this matrix function changes our vector into a matrix. We added one more argument in this matrix, which is n-col, meaning number of columns is equal to 2. So what's going to happen if we run this code? What we have is that first vector, 1, 2, 3, that's our vector A, 1, 2, 3. Then vector AA is 10, 20, 30, 40, 50, 60, 70, 80, 90. And we see that our argument, when we said we want 2 columns, automatically created 2 columns for us. However, when filling the data into the matrix, it fills it column-wise. In other words, it fills it from top to bottom and left to right. So that's why we see A, our first vector, is in the very beginning of this matrix, and AA, because it's longer, is finishing and then spilling onto the next column. Next, let's look at B. Matrix B is simply a very short vector ABC, and we're turning it into a matrix using the matrix function. Let's use C, and let's use D. Now, do we see anything strange about matrix B, C, or D? Well, matrix A is filled with numeric values. Matrix B is filled with character values, which appear as characters indicated by quotation marks. However, matrix C was a factor, but when we change it into a matrix, it becomes the most basic version of a factor, which is actually character. So in other words, the matrix function changed our factor data into character data automatically. Another thing is the matrix cannot take complex data types. That's why the matrix function cannot accept a factor data type, so it changes it to a more simplified version, which is just a character. The date data type, which was held by D, has also been changed. However, D is changing to its very basic form, which is actually a number. What does this number indicate? This number indicates the number of days after January 1st, 1970. Because of this, it's very difficult for us to read as humans, but the way that the computer is reading this number is calculating the number of days after a specific origin date. Usually, that origin date is January 1st, 1970. There are some exceptions to that rule, but we won't get into that during this course. So, we see that the matrix function has changed more complicated data types into its more simplified form. When we extract from a vector, we only need one index value. Why? Because a vector is a one-dimensional object. That means we just need to know where on that one dimension we want to extract data from. However, a matrix has multiple dimensions. Specifically, a matrix has 2 dimensions. So we have to use 2 indexes. The first index is the row, and the second index is the column. Right here, we have a shorthand for the row number before the comma and the column number after the comma. Okay, so let's see. In our A, we had 1, 2, 3. In our matrix A, we have 1, 2, 3 as a column. So if I said 2, 1, which value am I selecting? Well, I'm selecting row number 2, which is here, and column number 1, which is, well, we only have one column, but it's right here. So that would be where the row 2 and column 1 meet, which is this value here. So if I run this code, we should get that value right from here. It's being extracted from the matrix. Let's clear our console. Next, if you remember, we have a much more complicated matrix here. That looks like this. Here we have 2 columns and 6 rows. So here, if I'm extracting 2 and 1, that would be, again, row 2, column 1. We would get the same 2 from right here. Let's say I wanted to extract this 80. How would I do that? Well, I would look at the number of rows. This is row number 5, and this is column number 2. So if I change and I say row 5, column 2, I should get that 80 as a result. So the same with matrix C, the same with matrix D. We're extracting the middle value, row 2, column 1. If we use this str function, it gets us the structure. And in this case, we're using a matrix. So what is the structure of our matrix? We get the result. It's numeric, meaning the values inside the matrix are a number. And we have rows 1 to 3 and column 1. Then it gives us the values, the first few values in our matrix. If we had a longer matrix, such as matrix AA, now it shows us we have rows 1 to 9, only 1 column, and these are the first few values of that matrix. Let's look at the mode of our matrix. The mode of our matrix is numeric because the values inside the matrix are numeric. What would happen if I use the function class? It tells me that it's a matrix. So what's the difference between mode and class? Mode is telling me what's inside the matrix, and class is telling me what the object class is. The object class is a matrix. So it tells me that it's a matrix, and a matrix is a 2-dimensional array. So depending on if you want to know the type of object you have or the type of data inside the object, you might want to use mode to find out the type of data inside the object, or class to know what type the object is itself. Here is our data, 1, 2, 3, 10, 20, 30, 40, 50, 60, 70, 80, 90, right? We have 12 values here. And I'm going to turn that into a 3-dimensional array. A matrix is 2 dimensions, rows and columns. An array is a multi-dimensional object. Here's our array, and we're indicating that we want dimensions 2, 3, 4. The first value is the number of rows, same as with a matrix. The second value is the number of columns, again, same as a matrix. And now we have a third position here, which tells us how many values to add in another dimension. So what does that mean? In this case, we have 3 dimensions, rows, columns, and a third dimension. All right, so you can imagine this as kind of a block of numbers. So here we have one matrix, then we have a second matrix, then we have a third matrix, and a fourth matrix. Okay, so the first value is the rows. So we see this index is telling you that 1 comma, that is a row. That's the first row. Here 2 comma is the second row. This is telling you it's a column. We have blank because rows are first. This is not a row, it's a column, so it's the second position. In other words, after the comma. We have multiple matrices here. 1, 2, 3. And you probably noticed up on top, this information is telling you which dimension you're looking at. The first comma is indicating before it is rows, after it is columns, and this is our next dimension. Here's 1, here's 2, here's 3, and here's 4 on that z-axis. In other words, this is 3 dimensions. These are the kind of the different pages or the different depth that we're looking into that third dimension. All right. Okay, so can we take it a little farther? Yes, we can add another dimension to it. So let's take our vector, BB, which is the alphabet. And what dimensions do we have? How many dimensions is this? This is 4 dimensions. You probably noticed my note over here. How do we know it's 4 dimensions? The first value is telling us rows. The second is telling us columns. The third is telling us how deep the third dimension is. And now we're adding a 4th dimension. And this is the depth of that 4th dimension. We have 2 deep. So let's see what that looks like when we print an array in 4 dimensions. Obviously, it's going to be a little bit difficult to visualize, but we can calculate it quite easily by just reading the indexes that we have on top. These indexes are referring to the rows and columns would be here, and you can see those indexed below. Then we have 3rd dimension, number 1, and 4th dimension, number 1. Our next result, 3rd dimension, number 2, and 4th dimension, number 1. Then we have 3rd dimension, number 3, 4th dimension, number 1 still. All right, so the 3rd dimension is 3 deep, but the 4th dimension is 2 deep. So if we keep going, we see we finished all of the 3rd dimension, but now it's starting over because we need to create the matrices for the 4th dimension. Here's 4th dimension number 2, 3rd dimension number 1, 3rd dimension number 2, 4th dimension number 2, again 4th dimension number 2, and now 3rd dimension number 3. We finished all of the dimensions, so that's the end of our array. What are arrays used for? They can be very useful in machine learning algorithms. However, luckily for this course, we don't need to be concerned about how arrays work. Indexing for an array works the same way. We just have to say the row, the column, and now we need to say, in addition, the 3rd or the 4th dimension, depending on how many dimensions your array has. There are no limits, virtually no limits to how many dimensions that your array has. However, it makes it much more complex and difficult to understand, and computations take much longer when you have a much bigger array. Okay, so if I use this structure function on an array with 3 dimensions, it tells me the number of rows. The first dimension is 1 to 2. The second dimension is 1 to 3. The third dimension is 1 to 4. Our mode tells us what type of data is inside our array. What would happen if I said class? I would get array. It's telling me what the object is, which is an array, whereas mode is telling you the data type inside that object. Next, let's talk about data frames. If you remember, A is numeric, B is character, C is a factor, and D is a date. Now, what we couldn't do with an array or a matrix, we can do with a data frame. This data frame has incorporated all of the complex data types that we've created. If I extract 2, 1, what am I extracting? I'm extracting row 2, column 1, same as a matrix. Okay. I can also refer to that same value. If we look up here, we have A, B, C, D at the top. These are our column names. On the left-hand side, we have 1, 2, 3. These are the row names. And everything in here is the values that we have. So we can access specific values using the index number, meaning row number 1, column number 1, or row number 2, column number 1, as we see here. We can also access the same information using the row number and the column name. What's the column name? In this case, it's A. So let's try this. We should get the same value, and again, we get that same value. We can also extract a vector from our data frame. Let's clear out our console. Okay, so In our next line of code, we have a data frame that looks like this. Here's our data frame. And if I add this $, it means give me a vector, specifically give me the column named A. So if I run that code, we see that I'm getting only this column A, 1, 2, 3, 1, 2, 3. It looks exactly like a vector does. If I say give me column A, index 1, what I'm doing is first I'm creating a vector for column A, and then I'm indexing not from a data frame, but from the vector that I took from the data frame. So as you see, this is a vector. Now I'm asking for the first value of that vector that I created out of my data frame. So that's just the first value of this vector up here. Okay, all right. Let's clear our console. Next, what if we look at the structure of our data? Here we're using that str function on the data frame. And this is much more useful because on a data frame, we have multiple complex data structures. First, we have A. Column A is a numeric data type. Column B is a character data type. Column C is a factor with 2 levels, X and Z. Next, D is a column in a date format. Okay, so if I use mode on my data frame, it tells me it's a list. If I use class on a data frame, it tells me it's a data frame. What this means is the way that R is storing the data frame, the contents of the data frame, it's storing it as a list. So this is not that useful. So the str, the structure function, is much more useful at understanding what are the different data types inside your data frame. All right, next we have lists. I'm not going to spend as much time with lists because they're a little less relevant for this course. Here's a list of A, B, C, and D. And here we see, here's list number 1, and it's our vector. Here's list number 2, it's our other vector B. Here's list number 3, it's our vector, and here's list number 4. The double brackets mean that it's a list data type. Lists are hierarchical, meaning we can have a list inside another list. If we have a list inside a list, we might see more and more of these brackets around them, indicating the hierarchy. All right, so here we have a list A, which is a vector, a matrix, and a data frame all inside a list. So let's see what that looks like. Here we have all of those data types inside the same list. Here's our vector, here's our matrix, here's our data frame. Okay, and we can even add an array to that. So here I can add a multiple dimensional array. However, it becomes very complicated to try to read the results. So this fourth part of the list is showing you that array. Indexing from a list like this with multi-dimensions becomes very complicated. We can even have a list with multiple data frames inside the list. So here we actually have a list, then a data frame, and within our list we have another list that's holding the same information inside the other list. So here we have a double list. So you can see that the indexing becomes very confusing very quickly. By extracting a specific value, we can use these double brackets to index from that list. So this is indexing list 1, value 2 from list 1. For fun, if you want to see much more complicated indexing, you can run through the following codes. For the purposes of this course, I don't find it necessary to go through these codes. Okay. So here, if we use this structure function, we see that we have a list of 4. And then it's showing us each list. The first one is a numeric vector. The second one is a character vector. Third one is a factor vector. And the fourth one is a date type vector. If we use mode, it tells us that we have a list. If we use class, it also tells us that we have a list. Okay, so let's talk about statistics. Specifically, let's talk about measures of center, measures of variability, measures of skewness and kurtosis, and we'll cover some other topics as well. So first, let's talk about measures of center. A measure of center describes the center of your data, the centrality of your data. So we can use the mean, the average, the median, the mode. Depending on what type of data, some measures of center may be more useful than others. So let's go into it in a little bit more detail. The mean is the most familiar statistical measure of center because it is the average. It is the sum of the data values divided by the number of data items. So for a population, we use mu to denote the average or the mean for the population. While for a sample, we call it x bar, an x with a bar over top of it. The formula used to compute them are given below. Now on the left, we have the mu. Here is our formulation. And quite simply, it may look complicated, but the formulation is very simple. xi is each value in our vector. So I denotes the index of that value. So the first value would be x1, the second value would be x2, and so on. So what the top of this equation is saying is, it is the sum, just add up all together, all of the values in our vector, and divide by n, which is the number of values in that vector. That gives us mu. Now, most of the time, we're going to be using a sample. Anytime you collect data, let's say, for example, you collect data through a survey, you're usually getting only a portion of the full population. The full population is very difficult to measure. Let's say, for example, we want to measure the average student height at a specific university. Let's say Sogang University, because I'm a professor at Sogang University. So let's say that we're looking for the average student height of Sogang students. Well, what does that mean exactly? Students come in and out of the university all the time. Are we talking about only registered students? Do exchange students count? Are we talking about only full-time students? What about part-time students? So when you start to think about it, it becomes much more difficult to define what our population is. So let's say we have a very clear definition of what the population is that we want. Enrolled students at Sogang University right now. Well, even then, it's not so easy to define the population, because what do I mean by the average height? Your height in the morning is actually slightly different, slightly taller than your own height the same day in the evening, because the pressure of gravity and other forces change our height ever so slightly throughout the day. So what does it mean to have an average height? It's very difficult to know what the actual population is. So instead, we can use a sample of the population, because that means we don't need to get the height of every student all the time. In other words, the population mean is often unknowable. It exists, but it's not possible to actually know what that is because of the nature of the world. So instead, it's much more practical to use a sample mean. A sample is part of your population. As long as your sample is representative of your population, then your sample mean can be pretty close to the population mean. So when we're dealing with data sets in R, almost every time we're dealing with a sample. So let's look at the sample mean, and we see the same result. The n is the size of our sample. The xi is, again, each value in your sample. Okay, so the I is the index for each individual, for each observation of your sample. So let's think about that same example of measuring the average height of all Sagang students. I might choose a large number of students randomly. Let's say we pick 100 students randomly and measure their height on any given day. Okay? Then the first student would be xi. The I would be the first index, so that would be x1, which would be represented by that first student's height. X2 would be the second student that we measure, and so on until we reach the end of our 100 students. Okay? We would add up the heights of all those students and divide by n. In our case, that would be 100 because we have 100 students. And that would be our sample mean, or represented by x bar. The median is the 50th percentile, or the midpoint, of ordered sample data. In other words, let's say we organized all 100 heights from the shortest to the tallest. If we counted through all of those people, right in the middle, we have two people, person number 50 and person number 51, right? So the median would be right in the middle of that 50th and 51st person, and taking the average of those two would give us the median. If we have an odd number of people, let's say, for example, we measured 99 people, then we could use that 50th person as the center point of our data. That 50th person, the person at the 50th percentile, would be the median of our sample data. So, step one, sort the data, so from lowest to tallest, and find the value of the n divided by 2 observation. If n is 100, we divide by 2, that would be 50. Next, the mid-range. The mid-range is not quite as useful as the median, but the mid-range can give us a general idea if we don't have a lot of information about our sample. The mid-range is simply the middle point between the maximum and minimum value of our data. It's only used when there's no other information available. So it's not a very reliable measure. Why? Because if our data is skewed toward one side or the other, then the midpoint is actually not very representative of the data. This can be a problem if we have really strong outliers. So for example, if we're looking at income, some people make a lot of money. So if we take the midpoint between the person who makes the most money, the person who makes the least money, that's going to give us a not very representative value of the income distribution that we're looking at. Instead, it's better to look at either the median or the average, for example, because that tells us more about our data. It's more representative. However, the mid-range can be used if we don't know anything else besides the maximum and minimum of our data. The geometric mean is very useful in certain circumstances. For example, it's very useful if you have time series or a growth rate. It mitigates extreme values by deleting the extreme values and can only be used if all the data is above 0. So if we have negative values, we cannot use a geometric mean. A trimmed mean is very similar to the normal mean, except we're trimming off the edges of our data. So for example, to calculate the trimmed mean, we first remove the highest and lowest k percentage of observations. So let's say we are trimming our mean 10%. So let's say our k percent is 10. That means we're removing 10% of our highest and 10% of our lowest observations. This cuts off extreme values. So in that case where we have someone making an extremely high amount of money, if we trim off 10% of the top, 10% of the bottom of our data, we eliminate those extreme outliers. This gives us a more representative look of what the majority of our data looks like. The trimmed mean is simply calculating the mean after deleting the extreme outliers of the data. let's talk about measures of center. Here is our data. 1, 2, 2, 2, 3, 3, 5, 10. So what is the average of this? We can use the function mean quite easily. What is the median of our data? We can use the function median. Easy to remember. Mode. R doesn't have a built-in mode function. So one solution could be to create your own function. In this case, I'm creating a function called getMode. GetMode is the name of my function, and I'm using the function, which allows me to write my own function. So when I want to use this function, I want to input a vector. So I'm just going to call it vec. And then we see these braces define what happens when my function is running. So what happens when I run my function? The input to my function, called vec, I use the function unique, which gives me the unique values in vec. Then I've got a unique vector, which is just the unique values. And then I'm saying, which max, give me the maximum number if we tabulate all of the values in my vector with the unique values that are in the vector. In other words, count how many of each unique value occur in your vector. Then give me the maximum amount, and that is our mode. So let's try this function. This part is called defining the function. And now that we've defined the function, now we can use our new function, which is called getMode, and my data is x. My vector is x. So let's run our new function, and we get 2. Is that correct? If we look up here, 2 occurs 3 times. That's the most common value. So it looks like our getMode function is performing as we expected. Midhinge is also not a pre-programmed function in R. So one solution is to create our own. So again, I'm going to create a function, input a vector, and this is what it's going to do. It's going to calculate the maximum number and remove any missing values. And it's going to calculate the minimum value after removing any missing values. And it's going to calculate the difference between the max minus the minimum. And then it's going to take that value and divide it by 2. And that gives me the midhinge of my data. Here, our function gives us 4.5. It is simply the middle point between 1 and 10. Next, a trimmed mean means that we're trimming a specific percentage off of our data. So in this case, our data is x. We have how many values? We have 4, 8, we have 8 values. So let's say I wanted to trim off some of the values of this data. Let's say I wanted to trim 1/8 of the data. All right, what is this doing? It's calculating the mean of these numbers in the middle. So let's calculate the mean of just those numbers in the middle here. And we get 2.8333. Why? Because I said that I want to trim 1/8, so it's trimming 1/8 from each side of my vector. 1/8 would be one value from each side. Okay, what if I want to trim 2/8? That's giving me the same as deleting 2 from each side. So it's the same as this code here. What is this code here? That is my vector, and it's only the values from value number 3 to value number 6. These 2, 2, 3, 3. Okay, so the trimmed mean is not a separate function in R. It's an argument that we can use within the mean function if we want to use a trimmed mean. We can also change this into a specific percentage. So in this case, 2/8, obviously, 0.25. I can also just directly write 0.25. That gives me the same result. So let's say we were calculating the geometric mean. There's also no default geometric mean in R. Instead of downloading a library, we can again just define our own function if we know the formula for that function. So using the formula of the function, as long as our vector x is more than 0, use log on that value. So after taking log of our vector, making sure there's nothing 0 or lower, then add them all together, use an exponential of the sum divided by the total number of values in our vector. Length will give us how long the vector is. And then we use the exponential on it. This calculates our geometric mean. And here we have our geometric mean. Okay. This is useful for time series. However, in this course, we won't really get to time series data, so this is just for reference. So the measure of center tells us where the center of our data is, but the measure of variability shows us how much the values are either similar to that center or if they're dispersed and far away from that center. So how do we measure variability? Range is a very simple way to calculate how much our data varies. The range is simply the difference between the maximum and the minimum. This tells us where we can expect our data to fall. It falls between our maximum and falls between our minimum. It shows us the total range that our data covers. Variance and standard deviation are much more useful in statistics. What do they tell us? The population variance is defined as the sum of squared deviations from the mean divided by the population size. Sample variance is adjusted for sample size. Okay, so why is the variance much more useful than the range? Well, it's adjusted depending on how big our sample is, how big our data is. Okay, so let's again look at the sample variance, because in most cases, you would be dealing with a sample rather than a population. So let's look at the sample variance. The sample variance includes xi, again. Xi is representing each individual value in our data set. X bar, if you remember, is representing the sample mean. So this part of the equation is simply the sum of every individual value minus the sample mean. Well, what does this mean? It basically tells you the difference between each individual value and how far away that individual value is from the average of your sample. So if some of those values are very far from the center of your data, your variance is going to be much bigger. Then we take the difference of each individual value from the mean. Some of those will be negative, some of those differences will be positive, depending on whether your x value is above or below the mean. So we square that value, which changes everything into a positive number, because a negative multiplied by a negative equals a positive. So if we square a negative, it becomes positive. It also gives a slightly bigger weight to some extreme values. So on top of this equation, we have the sum of the squared difference of each individual value from the mean. On the bottom, we have the sample size adjusted minus 1. This adjustment is necessary because we're looking at the relationship between each individual value and the average. So it requires a small adjustment on the bottom. In other words, on top of the equation, we have the difference between all of the values and the center of our data. On the bottom of the equation, we divide by how much data we have. When we're looking at the sample variance, we use S squared. If we're looking at the population variance, that's represented by the symbol sigma squared. Again, it's almost impossible to measure the actual population variance, so instead, we often use the sample variance as an estimator of the population. Next, let's look at the difference between the center and the variability. The measure of center generally represents where most of your data would be, and your variability measures how close your actual data values are to that center. In our first example, we have a machine that is drilling a diameter of a hole that should be at 5.000 centimeters. In our first example, the consistency of our machine drilling a hole 5 centimeters is not very consistent because, as you can see, some of the actual values are above, some of them are actually below, and we see a big variability compared to our second machine. Machine B should be drilling a hole at 5 centimeters, but it's actually generally drilling a hole more closely to 4.99 centimeters. So what does this tell us? It tells us our first example is not very consistent in drilling a hole. The variability is related to the consistency of our machine. In our second example, our machine is consistent. However, it's consistently off of the center where it should be. So it probably needs an adjustment. So in that case, to fix each one of these machines, the diagnosis is a little bit different. One, the problem is with consistency. In the second example, the problem is with accuracy. That's how we can use variability and center to assess the situation and make better decisions. Measures of variability. So here is the same data that we had before, x. So what is the range of x? Well, our range from x is 1, 2, 2, 2, 2, 3, 5, 10. Our range is from 1 to 10, which is a total range of 1 to 10. The range function tells you the minimum and the maximum. So this is why we're getting 1 and 10, which is a little bit different than you might expect from the statistical function of range. Next, to calculate the variance, we can use the function var. Very easy. We don't need to remember or understand any complicated formulas. We can calculate the variance very easily. Using standard deviation, SD is standard deviation. And by squaring the standard deviation, that is the same as the variance. Variance is just squared standard deviation. Similarly, we can take our variance and get the square root, and that will give us our standard deviation, or we can use the function SD, that gives us the same value. So let's think about data. Here's an example of the average weight and the variability of that weight of newborns. Our second example is shoe sizes. The average shoe size is about a US size 10, and we see the frequency on the y-axis. The next example is male height. Most men are about 69 inches high, and we see the frequency on the y-axis again. The same goes with ACT scores. The same goes with retirement age of NFL players. The same goes with blood pressure. Okay, so what we see here is we're measuring totally different things, but we end up with the same distribution. This is a normal distribution. In a normal distribution, most of the data ends up around mu. What's mu? That's your population average. That's the average, the mean. Between one standard deviation below the mean and one standard deviation above the mean, we will have 68.26% of our population. Between two deviations below and 2 deviations above the mean, we have roughly 95% of our data, and 3 standard deviations below to 3 standard deviations above the mean, we have 99.7% of our data. Why is this normal distribution so useful? Because it happens to be a fact of nature that many data sets fall into this normal distribution. Because of this nature of the world, we can standardize our data so that we can compare values in one distribution to another distribution if they're both in a normal distribution. To do that, we can use this standardization formula. The standardization formula works like this. We take our xi value, which is each individual value, minus the x bar, which is the average of our sample, divided by s. S is the standard deviation of our sample. And this gives us a z-score for each individual value in our data. What does this z-score tell us, and why is it useful? The z-score tells us how close that individual observation is to the average of our data, to the sample mean. If it's above the sample mean, this z-score will be a positive number. If it's below the sample mean, our z-score will be a negative number. And we can know one more thing about it, which is how many standard deviations our z-score is from the average. This tells us how much that individual observation varies from our mean. Because the normal distribution is so ubiquitous across measuring many different attributes of many different things, it's very useful to standardize data so we can compare individual observations across different attributes. This also allows us to identify any unusual observations or outliers. Outliers are defined as any values with a z-score more than 3 or less than -3. In other words, if any individual observation is more than 3 standard deviations away from the center, the mean, we consider that as an outlier of our data. If it's outside of 2 standard deviations, we consider that as just an unusual observation. Why? Because if it falls outside of 2 standard deviations, 95% of data falls within 2 standard deviations of the mean, so only 5% of data observations would be outside of those 2 standard deviations. So how many are outside of 3 standard deviations? Less than 1%. Actually, only about 0.27% of data should be outside of 3 standard deviations from the mean. How do we know that? Because of the empirical rule for a normal population, we can estimate exactly what is the probability of a specific observation value occurring. We'll come back to that later in the course, but this is a very fundamental concept in statistics and allows us to make a lot of inferences about a lot of different types of data. Standardized data. Again, there is no built-in function to standardize your data. You can always use a package or a library to do this, but I like to create my own function so that I understand exactly how it works. In this case, again, I'm defining my function. My input is x. So this x would probably be a vector of some kind. So I take x and all the values of x minus the mean of x divided by the standard deviation. Okay, this is just our z-score. So if I standardize x, I get these standardized values. This one is telling me that my first value, 1, is minus 0.86 standard deviations below the mean. Minus 0.52, this is telling me that 2 is 0.52 standard deviations below the mean. My last value here is my 10. So this 10 value is 2.25 standard deviations above the mean. Okay, so let's take our data and plot our data. So I'm going to plot x. And PCH means the point character. It just means it's going to draw a circle that's filled in with color. CEX tells me the size. This is what our data looks like. We had 1, 1, We had 3 2s, we had 2 3s, we had 1 5, and we have 1 10. So it's just plotting these indexes, and the values are on the y-axis. Does that make sense? So now let's look at standardizing. Instead of green, we'll use hot pink, and we'll use the standardize function on x. What's going to happen? Is it going to look very different? It looks exactly the same. It maintains the same distance, but we see that on the y-axis, it changes just the values that we're giving to it. What are the new values? Well, 0 indicates what? 0 indicates the mean. 1 indicates 1 standard deviation above the mean. 2 is 2 standard deviations above the mean. And our 10 value became the value 2.25 because it's 2.25 standard deviations above the mean here. Okay, so as you can see, standardizing our data is very useful because we maintain the same relationship between all of the points of data. The only thing that changes is the value that we give it. We call that value the z-score. And that z-score gives us a lot of information about how close or far away that value is from the mean. As I said, there is another way we can standardize data. There's a function in this package called dplyr. And if I run this, it's going to ask me which server should I use to download this package. So I'm going to select, currently I'm in the US, so I'm going to find the United States, and I live in New Jersey. So I think this one is probably closest to me. Pennsylvania, okay. And that just means the closer you choose, the faster it will download. All right, so we see that it's already been downloaded. This install packages function means you're downloading the package. A package is just a set of functions that somebody else has made. And this one is being downloaded to the computer through the function install packages. Library installs that from my computer into my R session. So anytime that I want to use a specific function from a package, I need to use this library with the package name in order to load the function into R. This install packages function, we only need to use once to put the package onto our computer. After we've used it once, it's always on our computer unless we go in and change our directory or delete the file for some reason. So as long as the package is on your computer, all you need to do is write library to use that function. The install packages obviously requires some sort of internet connection, whereas the library function does not. Why? Because the library is bringing the package from your computer into the session of R. So in dplyr package, we can run the code called scale. That will give us a very complicated result. However, in order to get just the z-scores that I want, I can use the function scale and then use just column number 1 because that is where the information is that I want. So I'm going to use this function here, and that gives me exactly the same results as my homemade function, right? Cool. Percentiles. Percentiles are data that has been divided into 100 groups. For example, if you score in the 83rd percentile on a standardized test, that means that 83% of test takers scored below your score. Deciles are data that has been divided into 10 groups. In other words, it's the top 10% of data, then the between 10 and 20% of data, between 30 and 40% of data. Deca means 10, so we're splitting up the data into 10 groups. Quintiles are used when you're dividing into 5 groups. Quartiles are used when you're dividing your data into 4 groups. Percentiles can be used to establish benchmarks for comparison purposes. Percentiles refer to percentages where there are 100 groups. Deciles are really useful in finance because it gives you a very rough estimate of which group, which bin of data they fall in. The top 10%, the bottom 10%, and so on. So what about quartiles? Quartiles are scale points that divide the sorted data into 4 groups of approximately equal size. So the bottom 25% of your data falls between your first quartile, Q1, and the minimum of your data. Quartiles can also be very useful for visualizing data into a box plot. So the middle 50% of our data, meaning 50% of values fall within Q1 and Q3, is very useful for visualizing where most of our data falls. Then the extreme 25% on the low and high end can be considered between the minimum in Q1 and Q3 and the maximum of your data. We call this middle 50% of data the IQR, or the interquartile range. This is essentially a trimmed mean where K is set to 25, meaning we're trimming off the top 25 and the bottom 25% of our data. You can consider quartiles as a method of medians. For example, Q2 is the median between the minimum and maximum values in your data set. Q1 is the median between the minimum and Q2. In other words, it's the median between the minimum and the median of your total data. Q3 is just the same, but on the upper end of your data set. So Q2 is the median of all of your data. Q3 is the median between Q2 and the maximum of your data. We call this the method of medians because each quartile is a median, and the Q1 and Q3 are a median between the minimum and your median and the maximum and your median of your total data set. So why is this so useful? It's very useful for visualizing data in a box plot. These box plots are very useful because the IQR in the middle shows us where 50% of the data lies. These sticks on the end, which are actually called whiskers, sometimes this is called a box and whisker plot. These whiskers show where the upper and lower 25% of data lie. So if the upper whisker is longer, that means that we have a longer right tail, which is shown up here. If the left whisker is longer than the right, then we have a left skewed distribution. So the size of the whisker can easily show us whether our distribution is skewed to one side or the other. If our data is uniform, we'll see that those whiskers are a little bit shorter. However, if our data follows a normal distribution, those whiskers will be quite a bit longer than our IQR. So using box plots, there are specific rules to identifying unusual or outliers in our data. The IQR is represented by the box in a box and whisker plot. So that box is 50% of our data. 50% of our data falls between Q1 and Q3. So the size of that IQR, interquartile range, is important in identifying extreme values. So if we take that IQR and multiply it by 1.5, so 50% bigger than our IQR, we have our inner fence. What that means is we take that distance and say from Q1 and below Q1, if any values are within the distance of 1.5 IQRs below Q1, we consider that as the lower fence. So anything outside of that lower inner fence, in other words, a value that's less than 1.5 IQRs below Q1, that would be considered an outlier as shown here. Anything outside of 3 times the IQR, lower than Q1, would be considered an extreme outlier. The same thing happens on the other side. So the upper inner fence is 1.5 IQRs above Q3, and the outer fence, meaning anything outside of this outer fence, is an extreme outlier. This outer fence is established at 3 times IQR above Q3. It's simply showing the distance extremely higher than Q3 or extremely lower than Q1. Next, percentiles, quartiles, and box plots. The quantile function gives you 5 positions: 0%, the minimum, 25%, Q1, 50%, Q2, or the median, Q3, which is 75%, and the maximum, 100%. Quantile is useful for checking those Q1, Q2, and Q3 positions, as well as your minimum and maximum. If you want a specific quantile, we can add that using the probability. Using this quantile function, I'm asking for specifically only the probability at 10% and 50%, which gives me the number 1.7 and 2.5. What do these numbers mean? Well, it means that 50% of my data values are below 2.5. 50% of my data values are above 2.5. Okay. 10% means 10% of my data values are below 1.7. 90% of my data values are above 1.7. We can make a sequence between all numbers, all values from 0 to 1 by 0.01. What does this give us? This gives us all the percentiles. Okay? So if we want to know more detail about how this was exactly calculated, we can always use the question mark followed by the function name. In this case, the function name is quantile. That will bring up a menu. Let's make it a little bigger. That will bring up a menu here, quantile, stats. Stats is a base package that's pre-installed whenever you install R. Quantile is the function name, and this tells us how that function works. If we look through here, it tells us all of the arguments that can be changed. This defines all of those arguments. And if we look down here at the details, we get some specific explanation about exactly how that function was calculated. If we come down here, there are quite a few different variations on using this function. If you want to know where the information for how these calculations were developed, there's usually some references at the end, such as this. This will give you a better explanation of why the calculation was formulated exactly the way that it was, and any variations there may be on that formula or the function. So I always urge you, if you don't fully understand how a function works, always check the references and the arguments to make sure that you're using it the way that you expect and intend to use that function. All right, so let's plot our quantile. So in other words, let's plot the results here and see what that looks like. And we get what looks like a step curve based on what data we have. So our index before we had 1, 2, 2, 2, 3, 3, and we see that this curve kind of follows that same structure, right, when we plotted them. Summary will give us some key statistics, which is very useful. It's giving us our first quartile, Q1. It's giving us our minimum, Q1, median, which is the same as our 50% quantile, which is the same as Q2. It's also called a median. We get Q3, and we get our maximum, Q4. And it also provides us with the average. So this summary function is quite useful when you're looking at vectors, when you're using vectors. And I think the box plot in R is one of the best, most useful functions for understanding data quickly. What does our data look like? Well, the minimum value was a 1. We had a few 2s, so most 50% of our data is around between 2 and 4. And then we have our upper whisker, and then we have an extreme value up here. What is this extreme value? It's 10. This is an outlier. Why is this an outlier? Because it was more than 2 standard deviations above the mean. So when we create a box plot, instead of having our whisker go all the way up here, instead, our whisker goes as far as the inner fence, the maximum value within that inner fence. Okay? So this is the maximum value in our data set that's within that fence. And then we get a big empty area showing us that we have an outlier way up here. This makes the box plot in R one of the most powerful tools for understanding univariate analysis. So let's talk about skewness. The first moment of your data is your center, the mean. The second moment of your data is your variance. And the third moment is your skewness. So what does skewness describe? Skewness describes the shape of your data. If your data is symmetric, meaning equally on both sides, you'll have a skewness of 0. If your data is skewed left, as we see here, it means your skewness is negative or below 0. A left skew means that you have a long left tail. A right skewed data is a positive skewness, which is skewed right, meaning that you have a long right tail. Or in other words, most of your data falls on the left side of the distribution. How do we calculate skewness? How do we calculate this value? Skewness is calculated as follows. To calculate skewness, we consider the size of the sample of your data. We also consider the relationship between each value of your data, xi, and the distance it is from the mean, x bar, over the standard deviation of your sample. And this value is calculated to the power of 3 and then added all together for each value in your data set. And this will give you a negative number if you have a long left tail, or a positive number if you have a long right tail. And finally, the fourth moment of data is called the kurtosis. The kurtosis describes how thick the tails are on your distribution. And again, the kurtosis is 0 if it follows a normal distribution. If it's heavier tails than a normal distribution, we'll have a negative kurtosis value. If it is a more sharply peaked distribution than a normal curve, we consider that as a positive kurtosis. So the kurtosis describes how peaked or flat your data is. If your data distribution is flat, we call it platykurtic, like a platypus tail. If our distribution is very sharp and spiked, we call that leptokurtic. If it is following a normal distribution, we call that mesokurtic. All right, we have some measures of shape. So, unfortunately, there are no built-in functions for skewness or kurtosis. That's why I usually recommend this package, which is Financial Basics, F Basics. We'll load that package in. Then we can use the function called skewness. Here it tells us our skewness is 1.32. What does that tell us? Well, let's make a little histogram of x. And as you can see, we have a long right tail. So because we have a long right tail, our data is skewed, so our skewness is positive. How about our kurtosis? What does kurtosis refer to? It refers to how thick those tails are. All right, so in this case, we get 0.35. We have a positive number. So are we platykurtic or leptokurtic or mesokurtic? 0.35 is positive, Therefore, we are leptokurtic. All right, so this histogram function is very useful. We can use this histogram function, and again, it shows us how many frequency we have between the values 0 and 2, 2 and 4, 4 and 6. It gives us the shape of the data. One more additional note is everything that we covered so far was describing a univariate analysis. What does univariate mean? Uni means one, variate means variable, so one variable. However, if we have two variables and we want to describe the relationship, we have one more summary statistic that we can use to describe a bivariate analysis, which is the sample correlation coefficient. Correlation tells you how related two variables are. If they have a positive relationship, such as this example here, you'll see that they form a positive line, if we were to draw a line through our data, if we make a scatter plot from the x and y value. In other words, if we make a scatter plot and plot out each observation based on the value of one variable and the value of the other variable, if we put all of those together, we'll end up with something like this if we have a positive correlation. If we have a negative correlation, we'll see that we have a downward looking line if we drew a line through that data. If there's no correlation, in other words, there's no linear relationship, then we would have a zero correlation. The correlation refers to the linear relationship between the two variables. Let's call one x and let's call the other y. It doesn't matter what you're measuring, we're just labeling one variable as x and the other one as y. And to assess the relationship between these two variables, we can calculate the sample correlation coefficient. Again, if it's 0, it means there's no linear relationship. There could be a nonlinear relationship, such as an arc or a curve or a sine wave. However, if we do have a linear relationship, we might see plotted will look something like this if it's positive, something like this if it's negative. Let's say, for example, we have multiple variables. We call that multivariate. All right, so let's say we have multivariate analysis. Well, if we want to look at just two of those variables, here we have our three variables, x, y, and z. If I want to plot the relationship between x and y, it creates this scatter plot. So already, just by looking at the scatter plot, we can know the relationship between x and y. Is it a positive or negative relationship? Because we see them going downward, that means it's a negative relationship. In other words, as y increases, x decreases. And when x increases, y decreases. This is a negative relationship. It looks like kind of a downward slope. Okay. What about the correlation? We just looked at x and y. Let's plot it. The correlation is negative 0.89, meaning we have a negative relationship. Well, what if I switched it? What if I said the correlation y comma x? Do we get a different result? No, we get the same result. It's showing you the relationship between these two variables. Doesn't matter the order. It's telling you that when one goes up, the other decreases. And R has a really useful function called core.test. What does core.test do? It gives you a little bit more information about that Pearson correlation. So our correlation is minus 0.89. And way down here, we see that it gives us minus 0.89. But it also gives us a confidence interval, which tells us how confident we are that it's 0.89. Here's our confidence interval at 95%. We can change the confidence interval to 90 or 80 or whatever percentage you want to if you add it to the arguments of our core test. But this function gives us something more important. What's the most important thing it's giving us? It's telling us our p-value. This p-value is very important to tell us, do we have a really significant correlation or not? So this one tells us we have a significant correlation at the 5% level. We'll talk more about t-statistics, degrees of freedom, and p-values in a later video. Let's look at a different relationship. We checked the relationship of x and y. What about the relationship of x and z? Now let's plot their relationship. Oof, is this positive or negative or something else? Well, let's check our correlation. 0.23, that's a positive relationship. But is that a strong relationship? Let's see our core test. In our core test, we see that it tells us the correlation is 0.23, it's positive, but our p-value is not significant at the 5% level. What does that mean? It means there's no relationship between x and z. So this p-value is quite useful in trying to understand, is this useful? Is this correlation a useful number or not? Well, it depends. Is it significant or not? This core test function will give you that information. All right, let's say we have 3 variables again, slightly different. Now we have one called ZZ. It's just 1, 2, 3, 4, 5, 6, 7, 8. All right, if all 3 variables are correlated, let's check. All right, it looks like these are pretty strong correlations, right? Very high negative number. This one is a very high positive number. This one is a very high negative number again. All right, then we can use something called coplot, which is useful for seeing not univariate, not bivariate, but multivariate analysis visually. So let's look at this. All right, what we see here is telling you, given ZZ, so if the values of ZZ are between, I assume this is 0 and 2.5, then we see this first plot here. If the values are between, I think this is probably about 1, maybe a little bit more than 1 to about 3.5, it would be here. So this is showing us for the range of values of ZZ, we're seeing the range of values being plotted between x and y. In other words, it's giving you a 3-dimensional plot in stages, in slices. Okay, so this is what this is showing. All right, it's a little bit difficult to understand. It's a little bit more easy to understand when we're using real data rather than just 3 random vectors that I made. However, if you do have 3 variables and they're all correlated, it might be useful to use this coplot function to better understand their relationship. Thank you. So this draws a close to Lesson 4, Descriptive Statistics, from this lecture series. This lecture series is Applied Statistics Using Programming, and it's brought to you by Sogang University. My name is Dr. Ian, and it's been a pleasure. I hope to see you in the next video. Thank you. Sorry. I can use the function scale and then index column number 2. So, what? I can